Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place.
At around 400 BC, Democritus stated that matter is divisible only to a definite point. He said that a smallest piece of matter does exist. He named this atomos, which means indivisible.
Around 350 BC, Aristotle stated that matter is infinitely divisible. He was later proven wrong.
Dalton's atomic theory stated that matter is made of atoms. Atoms are indivisible and indestructible. Atoms of the same element are identical. Atoms of different elements are somehow unique, and atoms combine to create whole number ratios. This is what Dalton thought that the atom looked like. Dmitri Mendeleev went to University of St. Petersburg, and he was credited with the creation of the first useful periodic table in 1869.
John Newlands created the law of octaves in 1865. He stated that every eighth element would be chemically similar. He also predicted the discovery of some unknown elements at the time, like silicon, aluminum, and boron.
Thomson wanted to know how the cathode ray could travel to the other side of the tube if there were no gases in the cathode ray tube. He applied different magnetic fields to the rays. The cathode rays were deflected, meaning that it had both negatively and positively charged particles. The beam going from the cathode to the anode causes the fluorescent screen to glow.
In 1910, Robert Millikan created the oil drop experiment to determine the charge of a single electron. So this is the oil drop experiment, and this is the apparatus right here. And so at the top of the apparatus there is a positive plate, and then at the bottom there is a negative plate. And then what happens is they dropped droplets of oil into the apparatus, and then ionizing radiation is shot into it. And this causes the electrons in the air to attach to the droplets of oil. And then by adjusting the voltage, it can make the electrons actually like suspend in between the two plates. And so through this, he discovered the charge and the mass of the electron.
In 1909, Ernest Rutherford, before creating his gold foil experiment, knew a lot about radiation. He knew that the particle alpha was large and positive, and the particle beta was small and negative, and the particle gamma had no mass and no charge. This is the gold foil experiment. He shot alpha particles into the piece of gold foil. He expected them all to pass through because the particles are so large, but some bounced back. So he concluded that there was a larger particle in the way. Through this experiment, he discovered the nucleus. This is the nuclear model that Rutherford came up with. This is the nucleus, and he said that it was dense and positive. He also thought that the electrons were just floating in the atom.
James Chadwick, a pupil of Rutherford, discovered neutrons.
The nucleus is made of protons and neutrons. Protons are positively charged and determine the identity of the element. They're also called the atomic number. Neutrons have no charge, and protons plus the neutrons equal the mass number. Electrons are not found in the nucleus and are negatively charged. The number of electrons equals the number of protons. Isotopes are the same element with different number of neutrons. They may have different masses.
The discovery that light is quantized helped Niels Bohr develop the next atomic model. The next atomic model helped understand the position of electrons in the atom. This is Bohr's model of the atom, and in the middle is the nucleus, and it's made of neutrons and protons, and then around it are the energy levels where the electrons are located. Whenever electrons get excited, they jump to the higher energy levels. And whenever they calm down, they go back down to the lower energy levels. And when they do this, they give off energy. The equation to determine the amount of energy given off by an electron going from one energy level to another is En equals negative 2.178 times 10 to the negative 18th times 1 over n, which is the energy level, squared. This is the equation I just talked about with the energy of an electron. And so, for example, if an electron was going from the 6th energy level to the 2nd energy level, it would look something like this. This would be used to find out the difference, the change between energy levels.
The Heisenberg uncertainty principle states that there is a fundamental limit to how precisely we know both the position and momentum of an electron simultaneously. The Heisenberg uncertainty principle states that there is a fundamental limit to how precisely you know both the position and momentum of an electron simultaneously.
The Schrödinger equation is used to find the allowed energy levels of quantum mechanical systems.
There are 4 variables that are the quantum numbers that make up the identity of an electron. The first one is the principal quantum number. The second one is the angular momentum quantum number. The third one is the magnetic quantum number. And the fourth one is the spin quantum number.
The first quantum number from the 4 variables that identify an electron is the principal quantum number. This is the symbol used, and it can be a whole number greater than 0, like 1, 2, 3, or 4. It's the energy level and the size of the energy level in the atom. The second quantum number of the 4 variables found to identify an electron is the angular momentum quantum number. This is the symbol used, and it describes the shape of the orbital. The quantum numbers can be between 0 and n-1.
The first angular momentum quantum number is L equals 0. It is a spherical shape and is represented by the letter S.
The second angular momentum quantum number is L equals 1. It is in the shape of a dumbbell and is represented by letter P.
This is the third angular momentum quantum number. It is L equals 2. It is a clover shape and is represented by the letter D.
This is the fourth angular momentum quantum number. It is L equals 3 and the awkward shape. It is represented by letter F.
The third quantum number of the 4 variables that identify an electron is the magnetic quantum number. It is represented by m sub L. The orientation of the orbital is what it describes, and the quantum number is from negative L to positive L. The fourth quantum number of the 4 variables that identify an electron is the spin quantum number. It's represented by m sub s, and it describes the spin, and the quantum numbers are -1/2 and +1.
The Pauli exclusion principle states that no 2 electrons in an atom have the same 4 quantum numbers. The S's have 2 electrons, the P's have 6 electrons, the D's have 10 electrons, and the F's have 14 electrons.
The Aufbau principle states that electrons will occupy the lowest energy orbital available.
Hund's rule states electrons occupy empty, degenerate orbits before pairing up.
Thanks for watching!
Dalton, Thompson, Rutherford, and Bohr.